So let's see. Top view and side view. The figures above represent different views of two long straight horizontal wires, 1 and 2, carrying currents. Current 1 equals I and current 2 equals 2I, respectively, in the direction shown. The wires are held in place. In figure 1, the current in wire 1 is directed out of the page, and wire 1 is a distance d above wire 2. Point P is on a horizontal distance d from wire 1, and that same distance d directly above wire 2. Express your answers to part A and B in terms of I, D, and physical constants as appropriate. Use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. All right, so direct application of Ampere's law. I need an Amperian loop that I can use to determine the magnetic field from wire 1. So I'm thinking just a circle that has a radius of d. That look good for you guys? So, oh, no, not that. Let's choose that, and make it a circle, not a square. There we go. That look good to you guys? So I'm just ignoring. Oh, great, good job, Ms. Shelton. Good job. I'm just gonna stay there. All right, so that's my Amperian loop. Then Ampere's law is mu naught I enclosed times the sum of B dot ds. So the magnetic field has to be wrapping around the wire in this direction based on my application of the right-hand rule. So I'm also going to have my ds go in that direction. That way ds and the magnetic field are aligned, and my dot product will produce a cosine of 0 degrees. That all good for you guys? These evaluations I think are important. I'm just talking all the pieces out. So that allows me to take mu naught I and change this to I, because wire 1 has current I1 in it, which is just I. And I'll have the integral of B times ds times the cosine of 0 degrees. Strip away the vector information. Since I am equidistant away from wire 1, I think the magnetic field will be a constant everywhere around that loop. So I can factor B out and just do an integral of a circle, find its length. So I could break ds up into r d theta, but we're just adding up the entire length of a circle. So I'm just going to go from 0 to 2 pi d. Set those as my limits and integrate to get that b times 2 pi d equals mu naught I. And we're to solve this for the magnetic field. So b equals mu naught I over 2 pi times d. Now, how much of this do you have to show? I'd say most of this. Yeah, it's a derive. So you have to at least start with your fundamental principle and make the appropriate relevant decisions. The size of your loop, how your loop is arranged, all those kinds of things. Any questions about those choices? All right. B, derive an expression for the magnitude of the net magnetic field at point P. Well, we know we currently have a magnetic field that is this way at point P that is equal to mu naught I over 2 pi d. But wire 2 also is producing a magnetic field. And so looking at wire 2 and the direction of the current, and I'm going to look at the other picture now, I think that we have a magnetic field that way. That's got to be 2 mu naught I over 2 pi d, right? Because the current is twice as big. Does that make sense? All right. So unfortunately, neither of these pictures give us the full view of what's happening. So I want to kind of turn it to the side and recognize that we have a magnetic field that is this way, that is 2 times mu naught I over 2 pi d, and this is side view, so this way, that is just mu naught I over 2 pi d, and they are at right angles to each other. Does that make sense? So we just need the magnitude. I'm going to use Pythagorean theorem, but I'm going to factor out the mu naught I times 2 pi d to find out what that is, the net magnetic field at that point. All good? Any question about what I'm going to do? Okay. So it looks like it's going to be mu naught I over 2 pi d times the square root of 5. 1 squared plus 2 squared. So angle to the horizontal. I think that's this angle. So I'm just going to use tangent. So tan theta equals a half. So what is that, 33 degrees or something? I don't know exactly. Can somebody tell me? Yeah. What was that? 26. Okay. All right. I guess we'll keep going. Wire 1 is now released. Which of the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? Assume gravitational effects are negligible. All right, well, let's look at, I think this picture is probably the one to use. The magnetic field due to wire 2 has got to be into the page on this side of the wire and out of the page on this side of the wire. Would you agree with that? So if I use IL cross B in my right hand rule, it looks like on this side of the wire, there's a force that is this way on the wire. But on this side of the wire, the force is this way. So I believe that there'll be a force this way here and this way there. Are you in agreement? I mean, it's really hard to do it up there on the board. I just turned my paper sideways and kind of did this for one side and then this for the other side. It was definitely easier than trying doing it aligned like the board. But you guys, find a way to set it up. I mean, also, if I do it like this, it might be easier for us. This way on this side. Oops. Wire 1. All right. This way on this side of the wire, and this way on this side of the wire. Either way, that suggests the wire is going to twist as it falls. So let's see. Wire 1 will not move. I don't think that's true. Wire 1 will move upward as viewed in figure 1. No, it won't. Wire 1 will move downward as viewed in figure 1. I don't think so. Wire 1 will rotate clockwise as viewed in figure 2. I think that's true. Wire 1 will rotate counterclockwise as viewed in figure 2. No. Now, we might want to also think about this one spot here. Are there any components of the force on wire 1 that are up or down? Well, hear me out. Isn't the direction of the magnetic field right here on wire 1 this way at that instant? And the direction of the current is that way. Does that produce for that instant a upwards or downwards force? We're talking about right here, just the one spot, the spot that's tangent, where the magnetic field isn't going up or going down. Because here, the magnetic field is going down on this side, it's going up here, but right here, what's the direction of the magnetic field? It's gotta be that way, right? And the current is this way. So at that single point, there's a downward force. Do you guys see what I'm talking about? So there's more than one checkbox to check, I think. Yes, sir?
For wire 1, at that point, isn't the current downwards technically? So the magnetic field doesn't.
Let me make sure you might have me. Oh, you're right. Wire 1's on top. Golly, even I'm getting confused. So the magnetic field from wire 2 is this way, and the current is that way. So that'd be no force. Thank you for correcting me. So I think we're done. Just the one checkbox. Now it says justify your answer. Boy, I think we've talked that a lot. I don't think we have to justify any more than that, do you? You'd have to actually write that out, but I think we've done some justification. I want to show you something while we're doing this. Not on that side. Let's go to this side. The next part of this problem that I left out asked you to calculate magnetic flux. We've not talked about magnetic flux, but you know what magnetic flux is, right? Well, let me say that different. You know what flux is. So if you know what flux is, saying magnetic flux shouldn't be that big a deal. They had a problem like this with a distance like here, A, and a distance here, B, something like this. And this was like length L. They said there's a current here, and they asked for the magnetic flux through the square of wire. Would you know where to start that problem? Yeah? Well, we already have a expression for the magnetic field from the wire. All right, that's what we would have gotten from Ampere's law. And based on what I'm seeing in this picture here, the magnetic field would be out of the board on top of the wire, but getting weaker. Right? So it's getting weaker and weaker as we get further away from the wire. Flux is just how much magnetic field or any field flows through an area. This is our area. We're just trying to find out how much flux passes through that area. So I'm thinking maybe you don't know how to do that, and that's something we probably should talk about. Maybe not today, and it won't be on your test, but that was the second half of this FRQ. And its definition of flux is still the same. Flux isn't about Gauss's law. Flux is just a calculation. So in this case, there'd be no circle here because it's not a closed bounded surface. It's just a square of wire. It has a surface area inside that wire. Magnetic field passes through that wire. So you will need to be able to do this, and you will have to integrate. It's not a particularly hard calculation. It's not actually particularly hard to do, but it does involve having to put this in there and integrating from A to B in order to determine how much flux there is. It's where we're going in the future. So the word magnetic flux is something that we'll probably need to start bringing up, and understanding that flux isn't Gauss's law, but Gauss's law does use flux. All right. This solenoid, n total number of turns, and let's see, has a inner radius of A and a length of L. A power supply not shown is connected to the solenoid and generates a current I as shown in the figure. The top wires have current coming out of the board and the bottom wires have current going into the board. And we have an X, Y, Z that's kind of plotted on there. That would have been nicer if they had just been a little more, better about the Z, like maybe saying it's out of the board towards us, as opposed to having that Z at some kind of weird angle. It just seems more difficult than it had to be. The x-axis runs along the axis of the solenoid. Point P is in the middle of the solenoid. And we have an XYZ coordinate system. Assume L is much greater than A. Select the direction of the magnetic field at point P. Just based on the direction of one of these currents, out of the board means that the magnetic field around one of those currents has to be that way. And on the bottom, into the board means that it has to be that way. So it seems like it's in the positive X direction. So that's what I would have chosen here. Come down and say positive X direction. Justify my answer. Pretty sure I just did. And I think that that's a fair justification. All right. On the cutaway view below, clearly draw an Amperian loop that could be used to determine the magnetic field at point P at the center of the solenoid. You can't just draw anything. It would have to be rectangular. It would have to have a portion that lies along that axis line and a portion that is outside of the solenoid. But it would have to have that kind of shape to it. Anything circular won't work. Anything that is contained all the way inside also won't work. It has to look like this. Everybody understand? Yeah?
Square would look right.
Square would be fine. Square would be fine. Any other questions about that? You don't have to make it symmetrical. Like I don't have to have half of it here and half of it there. I just need to have a portion that's outside where I can indicate that the magnetic field is 0, and I need to have a portion that's inside where I can deal with just the magnetic field from the solenoid, and we already know that we won't get any contributions to Ampere's law through either of those sides. Using Ampere's law, derive an expression for the magnetic field strength at point P. Express your answers in terms of I, L, N, and A. All right. Mu naught I enclosed equals B dot ds. A, B, C, D. We already know the magnetic field is going in that direction. So I think it's in your best interest to show that this goes to 4 different integrals, one for each portion of your loop, because I'm sure in their grading guidance they talk about it. So A to B, B to C, C to D, D to A. Yep.
Should you not label requirements with A, because it's one of the variables they give you?
Okay. There. Does that make you happier? It makes absolutely no difference, but okay. Not an unreasonable request. Now, when integrating along X to B, then you would indicate that there is no contribution to Ampere's law because the magnetic field here is perpendicular to ds, and there's no magnetic field here. So that knocks out this one, and I don't know what happened to my D, but there we go. But that also knocks out this one. B to C, C to D, yeah. For the same reasons. D to X is knocked out because the magnetic field is 0, which leaves us with just one of them, which is the integral of B dot ds. If we say B is constant over that, it's just going to be the length of ds. Just assign a variable to indicate the length of ds. Or for me, I'm just going to write BC, the length of that line segment. On your mu naught times I enclosed. Mu naught times I enclosed. Well, we don't know the number of loops, but we know the number of loops per unit length. And we can multiply by the length and then multiply by the current. Sorry, that's kind of a mess. But we need to know how much current is enclosed. So number of loops per unit length and the length of the line BC. That gives us the actual number of loops that are contained in my Amperian loop. So the BC's cancel on both sides, but we'll get mu naught Ni over L times BC. Cancel those out, and B equals mu naught times the loop density times the current. And that's your magnetic field. No part of this has A in it because it's not dependent on where you are inside the solenoid. It's only true, though, if you can state that A is much smaller than L, which they stated at the beginning. And I guess I should use that little script L that they're using. All right. Next page. That's where the lab part goes. All right, so they start giving us all sorts of stuff. A is 0.015, N is 100, L is 0.4. The students connect the solenoid to a variable power supply. A magnetic field sensor is used to measure the magnetic field strength along the central axis at the center of the solenoid. The plot of magnetic field strength as a function of the EMF of the power supply is shown. Okay. On the graph above, draw a best fit line. That good for you guys? Look best fit to you? All right. So use the straight line to determine the resistance RS of the solenoid used in the experiment. Okie doke. Boy, could have made this a little easier on myself. I think I'll use that point and that point. Are those points okay for you guys? And that looks like it's at 1.6 and 4. And this looks like it's at 0.3, and if that's 1, then this is 0.5. Okay, so I'll get my slope. 1.6 minus 0.3 and 4 minus 0.5 gives me 1.3 over 3.5. All right, let's see how we're going to use that. B equals mu N over L times I. We don't have I, but we do have EMF over resistance. So I will back the R out and get B equals Q naught N L over R equals E, not equals, times E. There we go. So we know that this must be our slope. So mu naught N L over R equals 1.3 e to the negative fourth over 3.5 Tesla per volt. Okay. Is that enough, or do you need me to do the arithmetic? No, I don't have to do the arithmetic? Oh, good. Because I don't want to. But we have everything. We'll have to use the fundamental constant, mu naught, to be able to get that. All right. One of the students notes that the horizontal component of the magnetic field is 2.5 times 10 to the negative fifth Tesla. Is there evidence from the graph that the horizontal orientation of the solenoid affects the measured values for B? Yes. And it's because I would expect the magnetic field to go to 0 for 0 volts, and it doesn't, right? I have a y-intercept. That y-intercept suggests that there's a magnetic field there even when the voltage is 0. Do you guys follow what I'm saying? So that's pretty straightforward. Would the horizontal orientation of the solenoid affect the calculated value for RS? No. The calculated value for RS is based on the slope. So because it's based on the slope, it's not based on the y-intercept, the slope would be the same whether we had this offset due to the Earth's magnetic field or we didn't have this offset for the Earth's magnetic field. It would just shift all the points up or all the points down. So that would not affect my value for R. I bet these were only worth a couple of points. Alrighty.